solution. So here, through this session, what I'm going to do is that I'm providing a solution to this carbon dioxide emission, which is killing your society. It is not only killing your earth, not only killing your earth, but also it's killing your environment and everything. So let's share the presentation. So I just want to say that I actually am a fellow from this Carmel. I worked 4 years there. So when I joined there in 2018 at the time of flood, so I actively involved in so many designs with my students, and which is actually got so many prizes from KTM and everything. So I remember everything when I take sessions in wherever I go. I remember everything. It's the sessions and classes from this Carmel institution is given to me. So what I'm going to do is that I'm going to give a 1.5 hour session. So what I am going to explain, I'm going to explain the whole section into 4 parts. The first 15 minutes, the whole session will be dedicated to why we need this technology. The next 15 minutes, I will explain about this product exchange membrane fuel cells. What are its principles? What are its applications? And after that, I will explain what we are doing here and on what state currently India is. Okay? So I'll share the presentation and we'll move on to the presentation and explain the concepts one by one. So if there is any doubt, last 15 minutes will be dedicated for this questionnaires. You can ask any questions from this relevant to this area. Thank you. So I'm sharing the screen. Is visible? It's visible to. Is that visible to everyone? Yeah. Okay. Okay. Let's start the topic that I'm going to explain. So here, what we are going to discuss is hydrogen fuel cells. What are the principles? What the technology is, and what is the applications where we can use this hydrogen fuel cells. So first of all, so I think all of you know that in 2025, July 7, there was a flood in Texas. So when we study this change, is merely because of two primary reasons: the warming climate and inadequate warning system. So what I am going to focus here is the warming climate. How the climate change affecting our environment, our air. So we know that. So when you consider a sudden or a small or slight change in the temperature will result in these phenomena. So you can say that there will be a change in rain and snow patterns, there will be stronger storms, there will be damaged corals, there will be rising sea levels. So all these phenomena are occurring only because of a 1 degree or 2 degree rise in the temperature of our environment. So we know that we are, when you consider the world, a lot of nations are there. We will provide something to change that. So when you consider this UNFSS, in 1992, in Rio de Janeiro, so we, there was an, we'll say that COP, Conference of Parties being conducted. So there, we talked about the stabilization of greenhouse gas concentration in the atmosphere at a level that could prevent dangerous anthropogenic interventions with the climate system. So I think all of you know this UNFSS conference and everything. So I'm giving you introduction, a basic way why we need this change. So last year also we faced so many calamities because of this sudden rise of temperature. So it is going step by step. Each day, if you are considering, if the temperature is being increasing, and we know that there will be so many changes in the environment because of that. In 1992, about 154 countries, they signed or they talked about the main objective was stabilize the greenhouse gas concentration in the atmosphere. So how will you prevent this dangerous anthropogenic effects in the climate system? So after that, we know that UNFSCC, after that so many COPs were, Conference of Parties were organized. So in COP 3, in Kyoto Japan 1997. They this is next. It is going to happen in 2025. This will be in Brazil. What is the main objective of this Kyoto Protocol was? So we have to consider the system in such a way that we have to reduce the amount of carbon dioxide, nitrous oxide, methane, sulfur hexafluoride, hydrofluorocarbons, and perfluorocarbons in the atmosphere so that the temperature rise in the environment can be prevented. So there were so many agreements made in that mechanism. In 1992, Kyoto Protocol we signed. What are the major things which we signed? There will be an international emission trading system. There will be a clean development system, and there will be a joint implementation. So the nations or the countries are being jointly forming their hands or jointly holding their hands to reduce the amount of carbon dioxide in the atmosphere. So this is also another agreement which is signed by France, the Paris Agreement, which is COP21, it's France. So there, the major agenda of the meeting is that to reduce the temperature below 1.5 degrees Celsius. So crossing the temperature 1.5 degrees Celsius, this will help in severe climate change impacts, including more frequent and severe droughts, heat waves, and rainfalls. So we have to limit that to a particular limit. This is also same thing which is studied or which is the major agenda of the conference which currently Paris during 21. So you have to understand that a sudden change or a small change in 1.5 degrees Celsius or 2.5 degrees Celsius will result in so many changes in our environment. So you can see that if it is 1.5 degrees Celsius plus 2 degrees Celsius global warming, what are the changes which will happen to the environment? So we can say if we consider species, 6% of insects, 8% of plants, and 4% of vertebrates will be affected. If it is 2% increase, 2 degrees Celsius increase, we can see that from 6 to 18% of insects, from 8 to 16% of plants, and 4, there is a sudden or there is a rapid change. There is a 0.5 degrees Celsius temperature rise. So we have to focus how will you reduce the amount of temperature in the atmosphere. So if there is a 1.5 degrees Celsius rise, you can see that the temperature will rise. So this will expose a lot of people in the region. It will also produce so many issues. So there is another problem is coral bleaching. So I think all of you know what is coral bleaching. The coral region will deplete. So this will also reduce as the temperature or will increase the temperature. This will reduce as the what they say, it reduces the overall harmony of this society. So the same thing, what we are going to do from that Paris conference meeting. So we have to, the main agenda was we have to reduce the greenhouse gas emission. So there will be a limit is being prepared or maintained by each. Provided that we have to reduce the greenhouse emission to a particular limit. And after that, we know that what are the major gases which is being in the atmosphere, and we have to understand that what percentage of emissions are being provided from each region. If you consider China, and this 15.94% is being, these greenhouse gases are being emitted. So we are in third position. We are emitting about 4.13 is a value of greenhouse gases that we are emitting in the atmosphere. So it's our task is also to limit this amount by a large value. So we know that I'm just explaining a brief description. This all the consider in introduction.
Okay, sir. I think the slides are not changing.
We have still the first slide. We can only
see the first slide.
Okay, sir. Please read, sir.
Sorry to interrupt.
Yes, sir. Is it visible now?
Yeah, I think it's.
I just show the slides that I just shared. Is it visible, sir?
I think it's 13. Slide number
13. No?
Okay. I'll slide show it. If it's not visible, if it's not moved, just please tell me, sir. From beginning. Sir, is there any change to slide?
I think it's slide number 2.
Is that on 3? Is that showing 3, sir?
No, still 2 second.
Okay, sir.
Now it
Now
becomes
it
full.
becomes full.
Okay, sir. Is it okay if I share the screen like this?
Yeah, yeah,
Yeah, yeah, it's okay.
Okay, sir. Thank you, sir. So here, oh, I was explaining so many slides. I explained. So I think you missed the slides. So these are the counter protocols which is being there. Then the Paris Agreement, which I explained. So currently, I just want to show that what happens when we consider our India. So about 4.13 for the global economy is considered, but 4.13% is from our side. So I think all of you know what is this greenhouse effect and all. They say there will be a large layer of carbon dioxide around this atmosphere. This will prevent this solar radiation which is incoming to the earth, which is preventing it to go outside. So overall temperature of the earth is being increased. This is what this greenhouse. This is what concept we are learning from the ninth standard. It will be very. You all know this familiar. So how will you reduce this overall heating? The only way is to reduce the amount of carbon dioxide which we are what is it we are leaking or we are producing in the environment. In the so the next concept we have to understand that this is actually a signed protocol. This is called as nationally determined contributions. So in Paris Agreement, the nationally determined to reduce the greenhouse gas emission to a particular limit. So in every nation, they have some targets between 2015 before 2030 what will happen, before 2045 will have to happen, before 2015. So every nation will have some targets associated with it. Based on India's nationally determined contribution, our target is that so we have to reduce the emission density of GDP by 45% by 2030. So compared to 2005, we have to reduce the emission density by 45%. So if we have to reduce the 45%, we know that majority of our power productions are occurring in fossil fuels, not in Kerala. In other states, majority of the power production, everything is happening because of fossil fuels. We have to reduce it by 40%. Then only we can reduce the amount of carbon dioxide which is being produced in the atmosphere. Also, we have to produce some additional trees, we have to plant additional trees, etc., to cover this carbon dioxide emission in the ground, carbon dioxide emission. So we are saying that we will achieve this by 2070, and our target is that we have to produce about 4.476 gigawatt of energy without this carbon dioxide emission by 2025. So this is a basic introduction. So you may know that I think all of you are clear that why we need an source which won't produce carbon dioxide so that we can reduce the global warming. So the first point is that why we need this hydrogen. Why we need this hydrogen? First of all, when we are using hydrogen, there won't be any carbon dioxide emissions. Second one, if you are using a compressed hydrogen, it will give you the maximum power or maximum energy content per unit weight. It is for hydrogen. It is most abundant. So if you are able to store it, then there are so many potential for storage. So this is the best fuel. And it is actually we can use as an industrial fuel. So that's why all of them are giving importance to hydrogen. Not only this hydrogen, we are giving importance to green hydrogen. So if you consider Kerala also, we are considering, if you consider, I think it's called Kozhikode, they are starting to produce some green hubs. So if you consider overall India, about 400 crores of amount is being funded to start these green hydrogen projects all over India. Our major task is reduces the amount of carbon which is being produced in the atmosphere. Our major task is that. That means we have to produce green hydrogen. So if you consider production of hydrogen, the easiest method is steam methane reforming. Steam methane reforming. So what happens is that when you are producing the hydrogen, a particular amount of carbon dioxide is being delivered to the atmosphere. So in order to reduce that, we have to use green hydrogen. So what is green hydrogen? The hydrogen which is being produced with the help of electrolysis by using renewable energies. For example, if you know that solar energy is there, we are using water. there won't be any energy if you are using non-renewable. We can't consider the green hydrogen. So green hydrogen is that hydrogen which is completely derived from renewable energy sources. Okay, so this is what our task is. So according to the statistics analysis, by 2050, tenfold times hydrogen is required. So yeah, so actually by 2030, our mission is that we have to produce about 5 megaton metric tons of green hydrogen. So what we are planning is about 6 to 100 gigawatt electrolysis installations are being made. So if you see that in Kochi also, there is a green hydrogen electrolyzer is there close to the airport. So based only because of that, we can have some about 6 lakh new green jobs. Then we can produce about 1 to 25 gigawatt of renewable energy for the green energy production. So these all are happening. We have this a plan. There is an we'll say that by 2050 there is a task or target that is from the government is there. So how we can do that? That's what our task. The first of all is that hydrogen production is there. So we have to consider so many areas where we can produce hydrogen, green hydrogen. We are talking about this other types of hydrogens are there, some brown hydrogen, grey hydrogen, pink hydrogen, other types. So we are focusing on green hydrogen. How will you produce this green hydrogen? How we can effectively use for this transportation and storage, and how we can use this. So this is what's the area. So actually, from this area, if you are considering hydrogen utilization, the research area comprises of hydrogen production, hydrogen infrastructure, hydrogen utilization, and hydrogen storage. What I am working is the hydrogen utilization region. Fuel cells, which is the major area where I am working is proton exchange membrane fuel cells. So I think all of you got an idea why we need this and the way in which we are at a critical stage now. By 2050, if we are not able to reduce this carbon dioxide emission by a limit, or our global warming will increase, automatically we can see that everything will change. So we are in a critical region, more critical situation now. Majority of the scientists are following this hydrogen production and hydrogen infrastructure. So hydrogen production is green hydrogen. Then how will you provide this infrastructure? So then how will you utilize this hydrogen and how will you effectively? So these all four regions are very, very important. So I am working in hydrogen utilizations where I am working in fuel cells. Mainly, I am working in proton exchange membrane fuel cells. So I'll give a brief description about what are the different types of fuel cells that we are having now. So when you consider fuel cells, you know that there are different types of fuel cells are there. It's completely based on the electrolyte and operating temperature. We are classifying the fuel cells. SOFC is called solid oxide fuel cells. Then molten carbonate fuel cells. We can see the temperature of the operating 500 to 1000 degrees Celsius. SOFS, solid oxide fuel cells. Then molten carbonate fuel cells are there. Phosphoric acid fuel cells are there. So based on the temperature, we have different fuel cells. But what I am working is proton exchange membrane fuel cells. You can see that it is operating at an 80 degrees Celsius. So if a machine is operating in 80 degrees Celsius, we can effectively use it for vehicles, for transportation, and also we can for the power generation or home, for portable applications, so many applications. So based on the membranes, if you consider these all fuel cells, only the electrolyte membranes are being different. So this is stabilized zirconia is being used in SOFC. So if you consider molten carbonate is using sodium or magnesium carbonates. So phosphoric acid is used as electrolyte this phosphoric acid fuel cells. In proton exchange membrane fuel cells, we are using I'll show the membrane. Then alkaline fuel cells, we are using KOH in water. So there is a temperature variation. If you have to use this hydrogen as a fuel in this temperature, the main option or the specific option that we have to adopt will be PMFC. So I'll just show you how a PMFC looks like. I have one cell with me. I think all of you can see that this is actually a 25 centimeter square proton exchange membrane fuel cell. This is actually 25 centimeter square. So when we are talking about the fuel cell, we have to mention its active area. It's very, very important. Why we have to consider active area is that active area is the region which will produce the current. So we are going to give hello. Am I audible to everyone? Hello.
Yes, sir, audible, sir.
Okay, okay. So what I'm going to do here is that I'm going to explain this proton exchange membrane fuel cell in detail. So I will explain what is this proton exchange membrane fuel cell, how this operation, how the working happens. If you consider an electrolysis process, we know that there will be an anode, there will be a cathode, and there will be an electrolyte. There will be an anode, there will be a cathode, and there will be an electrolyte. What happens? At anode, oxidation occurs. Oxidation occurs means electrons are being released from there. At cathode, these electrons react with this oxygen to produce some results. So for example, if you are considering this electrolysis of water, you can see that when electrolysis of water occurs, we know oxygen is being produced and also hydrogen is being produced. It is just opposite what is happening in a fuel cell. You can see the figure. Please look at the figure. So we are having a membrane here. Membrane means it's a solid, like you can see that a membrane like here. It's a solid membrane. So instead of a liquid electrolyte, we are having a solid membrane, and there are two layers are there. I'm providing some hydrogen here. So what happens is that when hydrogen reaches at the catalyst layer, this hydrogen will move through this membrane. At the same time, oxygen will move through this external circuit. It will reaches this cathode side where it combines with hydrogen and oxygen, producing water. This is the working of a proton exchange membrane fuel cell. I think all the concept is actually very simple. Hydrogen coming there, hydrogen split into H plus and electrons. These electrons H plus O reaches the cathode side. They will react together, and what happens is that water is being produced. So each time you know that it's completely based on how hydrogen changes to H plus and electrons, and also how electrons reacts with oxygen at this catalyst site. These factors governs the performance of the fuel cell. So what we are supplying on the anode side, we are supplying hydrogen, 99.999% hydrogen that we are providing. There is any sudden small change, there will be some there will be a decrease in performance. So we are using 99.999% hydrogen. This hydrogen reaches here, it splits into H plus and electrons. These electrons move through here. When it reaches here, this H plus and O combines to water is being produced. Not only water, heat is also produced. One of the critical factors will tell you that when a fuel cell operates, if I'm making a 1 kilowatt fuel cell, at the same time an 800 watts of heat energy is also being produced there. Not only power, but also the heat is also produced in a situation. So a thermal management system is very much required when we are fabricating a large fuel cell stack. So I think the concept is clear. Hydrogen splits into 2H plus and electron is being released. These electrons, oxygen combines with water is being formed. The overall reaction considered, the electricity is produced, also heat is being generated. This is just for the opposite of electrolysis of water. So here if you consider, we are having a membrane. This is called as proton exchange membrane. You can see that the electrons are not transferring through this region. Only hydrogen, the H plus ions are transferring. That's why it's called as proton exchange membrane. What is a proton? The proton is H plus. It can transfer. So that means when you are designing these membranes, so actually when you consider membrane, one interesting part I will tell you that no commercially available producers for these membranes are there in India. If you are considering a membrane, you have to go for any US markets or Korean markets or Japan markets. So they are producing in this company called as DuPont. They are producing a membrane called as Nafion. This is the only commercial available or maximum power producing membrane here. So many of the research institutions or the polymer engineers are working on this proton exchange membranes now. And also one more thing you can see that is a catalyst. This catalyst is another crucial factor. So here in our institution also we are developing a catalyst which will provide more output. Not only there is another mechanism in engineering perspective you are considering. If you are considering system, how will you assemble it? This is also another engineering opportunity area. So the next thing, I'm just explaining the structure of a battery to just get an idea how the fuel cell works. So if you consider the structure of a battery, we can see that we have an anode, we have a cathode, electrode, the same thing, and we can see a zinc carbon battery or a dry cell. So it is similar to that of working of a battery. You can see that. But what happens is that the battery, after the use, you have to chemical energy is being converted to electrical energy, and we have to throw it away. But what is consider a fuel cell? If there is a supply of hydrogen oxide, regularly if we are providing still the hydrogen oxide, then we can provide this, we can have this electricity. That's the advantage of this fuel cell. So I'm going to explain the components of fuel cell now. So I think the principle behind of fuel cell is clear to you. I think you already learned this concept in +2, but this is more elaborate way I'm explaining that. So if I consider the structure of a fuel cell, we can see that this is what a fuel cell looks like. So if I dismantle this fuel cell, if I'm dismantling this fuel cell, we can see that at the inside we are having two plates. It is called as anode end plate and cathode end plate. Anode end plate and cathode end plate. So we can ask why we are using this end plate. So end plate is just providing this structural rigidity to this whole system. And after that, we can say that a gasket is there. What is that? This is just providing the insulation. This is stainless steel material or aluminum material, 606 grade material. So we have this aluminum grade 606 material, and after that I have the gas insulation to avoid the contact with this copper plate. So next, after that I am having a copper plate. You can see that I can see that I think all of you can see that this is a copper plate. And after a copper plate, we can see that two graphite plates are there. So why these graphite plates are there? I will show you graphite plate. So these are custom made or machine graphite plates in our lab. So these are, you can see that one is having 25 centimeter square and another is having 6.25 centimeter square. So these two are CNC programmed and machined in our lab itself. So this is called as the lengths of the fuel cell. Why it's called as lengths? Because this region provides the hydrogen and oxygen to the central region, the electrolyte, the polymer electrolyte membrane. So what happens is that I will provide this hydrogen to this region. I will keep this membrane in between this region, and I will keep this one of the carbon plate one of the graphite plate will act as the anode, other plate will act as a cathode, and in between this region I have this membrane. In between this region I have this membrane. In between this region, we have this membrane. We call this one as membrane electrode assembly. We call it as membrane electrode assembly, and this is called as the heart of the fuel cell. So these lengths, I know we know that lengths will provide the gases, and in the center we are having this MEA. Reactions occurs in this MEA, and we will take this power we will complete the circuit with the help of this copper plates. So I will explain one by one. At the end I am having some anode plate, then I am having some graphite plate, I am having this membrane electrode assemblies. Close to the membrane electrode assemblies, we are having some gas diffusion layers. So we'll be together with that. Then we are having some gasket. We will make a sandwich. Then we will press them and we'll clamp them up by applying some torque. You have to understand one thing is that the stoichiometry in which we are providing the hydrogen. The stoichiometry when we are providing the operating conditions, the temperature, the pressure, the clamping load, the material, each factor controls the performance of the proton exchange membrane fuel cell. If there is any change in one of the material, the overall performance will decrease. So we have to give importance to all the components of the fuel cell. So the next thing I'm going to explain the components one by one. You can see that I already told you that what is this membrane. Commercially, the the material that we use is naphion. Based on this thickness, we have so many materials: naphion 117, naphion 212, naphion. So different varieties are there based on the thickness. So commercially now naphion membranes are not available in India. So there is another membrane that we are using now, which is called as PFSA B50. It has the same property similar to naphion 212. So what happens there? The H plus is being transferred through this membrane. So many mechanisms are there. Surface mechanism we call it as lotus mechanism, vehicle mechanism. There will be a how the H plus is being transferred from one region of this membrane to the other region. There are so many theories are there. Lotus mechanism is a theory. A surface mechanism is a theory. And vehicle mechanism, these all are theories. So how the H plus is being transferred from one region to another region. If you consider surface mechanism, this is H plus, you can see that it is moving along the surface. It is come here, and you consider the Gaussian mechanism, one of the section is transferring that to the other region. And if you consider the vehicle mechanism, it is like a vehicle, and this vehicle is transferring this H plus from one. These all are some theories put forward by some scientists. How the H plus is being transferred through a membrane. We call this as a polymer electrolyte membrane. Currently, the cost is very costly. We are purchasing a 40 centimeter by 40 centimeter cross sectional area. It costs about 81,000. We don't have any commercial fabric manufacturers here in India. If we have to make a product exchange membrane fuel cell, we have to import from other companies. So that's a good thing. So if you can, so many polymer engineers are there. They are working on this. How we indigenously develop this membrane. So after this membrane, the next thing is very crucial. Another cost-raising factor that we call as catalyst. So we know that what is the function of a catalyst and everything. It reduces the activation energy. So if there is hydrogen, we have to change this hydrogen into what? H plus and electron. So we have to change into ion and an electron. So there must be a catalyst to do that. So commercially, we are importing this catalyst, which is called as 40% platinum carbon. That means there will be a carbon will be there, and over that platinum will be block. You can see that this is a blue carbon block in which platinum is deposited there. So if you consider platinum loading, based on the performance we require, we will deposit maximum number of platinum. Sometimes 0.3 will be there, 0.4 will be there. This is completely based on the performance that we demand. So we know that if the cross section is very large, if we increase the amount of platinum, there is a chance of increasing. So each component is its as load. So if you consider platinum loading that we currently using is 0.2, 0.2. According to the community conference meeting, they told us that we have to reduce the amount of carbon. We have to reduce the amount of platinum so that we can make this more economical and useful to society. So what we are currently using is 0.3 milligram per centimeter square. If you do a simple calculation for this is not for only one side. This is on the anode side, we need 28 milligram. On the cathode side, also we need 28 milligram. So if we compare that, so we about 2,240 rupees required for fabricating a single MEA. The catalyst I am talking about, 25 centimeters square. Only for this catalyst we need this much. Only catalyst we know naphion solutions. So this makes us costly. So researchers are being going on how to make a catalyst without platinum, and how to make transition elements in the place of platinum. So some researchers are also going on this region. So I think the major part consists of this naphion membrane, then platinum catalyst. Then I will tell you a principle behind it. So if you consider a proton exchange membrane, there are three layers. There is a proton exchange membrane, a gas diffusion layer is there. Why we need this gas diffusion? When the hydrogen reaches there, it travels through this region and reaches this point. And not only this catalyst layer, there is so many naphion is also provided. This is called as proton exchange membrane triple phase boundary. Triple phase boundary means H plus is being created, electron is being produced, at the same time hydrogen reaches there. So these three occurs in a single region. As the number of triple phase boundary increases, the performance of the PEM will also increase. So you can see that the GD is called as gas diffusion layer. When you consider this graphene plate, at the end of the graphene plate, we have to use a gas diffusion layer. After the gas diffusion layer, we will have this catalyst, then only there will be a membrane. So the gas coming passes through the GDL, reaches the gas release, then the H plus has to cross the membrane. So three boundaries are being generated. As the maximum number of boundaries generated, the performance is increasing. So that's a major thing that we have considered. If you are adding so many catalysts, won't improve the performance. If you are increasing this hydrogen amount, won't increase. So the main thing is that when you are fabricating, we have to make sure that the triple phase boundary is being produced there. As the number of triple phase boundary increasing, the total performance of the whole system will increase. It's completely based on the triple phase boundary. So in order to create the triple phase boundary, what we are doing is that we will have some ratio. So when you can take the catalyst, we will make some catalyst ink, then we coat on this GDL. There are so many methods of coating the GDL. So sometimes spray coating, sometimes hand spray, hand just using brush we can coat it. Some ultrasonic coating machines are available now. So in many ways we can coat it. So when we are coating, there must be a consistency of this catalyst layer and naphthalene solution, which determines the triple phase boundary. So this is also a field under research. So next one, this is called as gas diffusion layer. We use carbon paper and carbon cloth as gas diffusion layers. These gas diffusion layers provides the hydrogen comes here. The hydrogen has to reach this catalyst layer on this right. So it has to pass through a layer. This is called as this catalyst layer, this gas diffusion layer. Sometimes it is made up of carbon paper. Carbon cloths are also available there. So it may be hydrophobic or hydrophilic. Majority of the time we will use hydrophobic so that water produced in that region will go out very easily. So three components I explained. First of all, this proton exchange membrane, we call it as polymer membrane, and after that we are having one catalyst. Then I talked about the triple phase boundary. Then the next region is gas diffusion layer. So what we are having is that we are having a platinum catalyst. We will spray coat, then membrane. So this is a three-layer structure. Three-layer structure means the membrane will be there. Then on the two sides there will be two catalyst layer, and over the catalyst layer we have the GDL. So it's a three-layer structure that we are having. So I already told you that membrane electrode assembly, which is called as heart of the fuel cells. So here you can see that three layers are there. So three layers means this is called as a membrane. Over the membrane we are having GDL, two GDLs, and over the GDL we have a catalyst layer. So these are the total, if you consider total 5 layers are there. 3 layers, membrane plus 2 catalyst layers. So total how 5 layers consider sandwich we will use. You can see a machine close to me, which is called as a hydraulic hot press, which is being used to press this component together. So based on the bonding also the performance depends based on the bonding also. So we will have some condition for the pressing also. So the 3 layer is a total 5 layer structure. So when after the fabrication, we will get a MEA like this. When we are having an MEA, we will denote this or we will define the MEA by its active area. Active area means where we caught the catalyst. Active area means the area in which the catalyst being coated. So here you can see that the black region is the area, and this is the region of the membrane where there is no catalyst being coated. So that is not the active area. Active is the region where H plus is being, H2 is being converted to H plus and electrons. On both the sides we are having this active area. And after that, so MEA can be different size. We know that when you are considering an MEA, the MEA are different size. Based on the area, we will define the membrane. So here we can see 1 centimeter by 1 centimeter square membrane is there. Also 5 centimeter by 5 centimeter. What currently I am working is 200 centimeter square. 20 by 10. 200 centimeter square. That means one of the membrane will produce close to 100 watt. One membrane will produce close to 100 watt. This is what we are working on. 200 centimeter square membrane. So 1 centimeter square membranes are there. Also 5 centimeter by 5 centimeters. So based on the when you consider research papers and everything, and scientifically, the majority of this scientists works on this 25 centimeters square. When you see the publication of everything, they are following a 25 centimeters square ME. And after that, I already show you the graphite plates. In graphite plate, you can see that the different types of flow fields are there. So we can see that different. This is called as serpentine. This is called as double serpentine. So based on the flow field, also the performance of a fuels can enhance or deteriorate. So first of all, being tried for parallel flow field. From parallel flow field, different flow fields are being tried. So these flow fields will enhance the performance. Now so many some advanced like interstated. So similar to our lens, some of them are designing certain blocks are there. So it's just I already told you that this flow field actually behaves as the length of this. So if we are providing more amount of hydrogen or more amount of hydrogen is able to convert into H plus electron, the performance will increase. So this is a crucial factor in this flow field. How we are providing this hydrogen here. So different types of arrangement is there. So in CFD, if you consider this arrangement, computational fluid dynamics is being used to analyze this flow field and how the performance is improved output we can easily predict. So we can't. So if you fabricate one fuel cell, it nearly costs more than 30 to 40,000 for a 6.25 or 6.25 to 9 centimeters square. I'm talking about the machining cost and all. If you are going for machining this CNC, if you are going to machine this particular component using CNC, it's very costly. So nearly in the last one we machined a 200 centimeters square. It nearly took 12 hours for a CNC machine to complete one cycle. So one cycle to complete 12 hours. That much the thickness is there. 1 centimeter depth, 1 centimeter width, 1 centimeter width. So it needs so much precision. The whole process occurs very slowly. So 8 to 10 hours, you can see that if it is a 350 watt machine, they will take about 350 to 400 per hour. So if you are fabricating this, it will cost more than 10,000 to 12,000 for fabricating a single side. So both the sides are considering it is very costly for machining this fuel cell, machining this flow field. So we can't experimentally try different. We can't experimentally try different flow fields. So what we will do is that we will do a CFD analysis. We will do the drawing, solvents or something softwares. Then we will do the analysis from multi-physics. It's a very user-friendly software that we are using for the CFD analysis. The CFD analysis helps us to understand what happens the with the performance when you change from one flow field to another flow field. If you go for the research papers, so many studies are going still they are changing the flow fields. Now some studies are showing that instead of this graphene plate, they are using stainless steel plates and they are using pressing the etching the flow fields. So many studies are going there. So here you can see that if you consider this plate, it's nearly 10 mm. So if you fabricate a uh, fuel cell stack, this is one cell. This is one cell. So you can imagine that if you are fabricating 10 cells, the whole size will be very large. So what we can do, we can reduce the size of this graphene plate. So what we can, our limitation is that our current technology in India, in other countries, they are fabricating this flow field with the help of stainless steel, some grades which prevents corrosion. So still now this technology is not available in India to commercially manufacture a single fuel cell with the help of stainless steel. So the whole system size will be very large. So if you consider some commercial manufacturers like Horizon and everything, they are fabricating these below 1 mm thickness. They are able to manufacture one graphene plate or sorry one stainless steel plate. Below 1 mm they are able to fabricate. That means you can see that the size of the fuel cell they can imagine. They can easily stack together about 50 to 60 cells easily. But if we currently, when we are fabricating here, we are fabricating about 50 cell stack. If we assemble that, it will be a big size compared to let's like the CPU of a system or something like that. Big than that. The next concept we have to understand the current collector plate. So we can see that when you consider the fuel cell, it's a 20%. I told you that. Here I'm having a copper plate. What is the function of copper plate? This copper plate will help us to take the current outside. So initially, when we start the research from scratch, what happened is that we used only copper plate. So what happens that the performance deteriorated. Copper plate has the properties of corrosion. It reduces the performance, and after that we are using gold plating now. We are providing gold plating of this copper plate, so that again the performance improved. Okay, so this is the next component. So membrane electrode assembly, and after that copper plate, gas diffusion layer. The last one is end plates. So you can see that this is end plates. Initially stainless steel will be used to provide a rigid structure. Now currently we are using aluminum 6061 grade, which will provide enough rigidity to the structure. What happens is that if we are not using the good end plate, there will be a bending at the center. If there is a bending at the center, the membrane electrode assembly won't perform very well. So this rigidity and the density of the material is a crucial factor when you are designing these end plates and nuts and bolts. So here you can see that instead we are having two large plates which is having about 2 centimeter length. So it's completely based on this nuts and bolts arrangement, which is holding the complete arrangement together. So many studies are there, still there, how this alignment of bolts are there. Here you can see that we are providing at the center, and he can CFD analysis can be done, or else we can use Abacus software to design that. So here also we can provide this bolts in this region, 1 2 1 2. So many different varieties that we can try. Then we can optimize the performance. This is another, sorry. So we will study the different loading, and we will insert some pressure Phillips inside it. We will apply some load, and we will check the pressure, whether the pressure is uniform everywhere. We will check that. We can here easily we can check the combination. We can easily change the combination, and we can study what is the best optimum clamping for this fuel cell. This is another study. So I already told the working principle. I think you can see the figure. So hydrogen, there will be an anode and cathode. You have to understand this is the GDL. After the GDL, I'm having this starting from the center. From the left hand side, I'm saying this is the just the miniature. Black represent the miniature of this flow field. Through the flow field, this hydrogen reaches. This is the region what we call as the GDL. After the GDL, I am having a region which is called as the catalyst layer. Then membrane. Then again GDL. Then again this GDL oxygen flow field. Hydrogen reaches here, it splits into H plus and electron. This H plus will move through the membrane, it reaches here, combines with oxygen, water and heat is being produced. So now how will you study this, how the current is being produced here? So if you simply consider this, if you have to analyze the performance of a proton exchange membrane fuel cell, you have to keep in idea that we know the Ohm's law. As here you can see that a cell is there. Parallel to the cell, I will collect a voltmeter. I can change the resistance value. Based on that, the current will be produced. So what will we do is that we will use some software to change the voltage value. Based on that, we will study the current produced. So when you study the performance of a proton exchange membrane fuel cell, the basic thing that we have to consider is what we call as polarization curve. What is a polarization curve? It's simple. It's a relation. It's a graph which is being got with the help of voltage and current which is being delivered. So we will take the voltage and current at different values, and we will plot the graph. So thermodynamically speaking, the net or the effective potential which has to be produced from a proton exchange membrane fuel cell at 25 degrees Celsius is 1.23 watt. So we know thermodynamics is speaking, but there will be some changes. Because of these changes, what happens is the graph will be something look like this. So after this section, I will explain why this straight line graph changes like this. This is the optimum one, 1.33 watt. So if you consider battery also, they have some particular voltage from a single cell. Like that, thermodynamically, if you consider the oxidation of hydrogen, And if you write the thermodynamics, we will get 1.23 volt. And this 1.23 volt, we will, when we assemble and execute the practice, we assemble and use it, there will be some losses. As a result of these losses, this graph will be looking like this. And you can see that using the current and voltage, I can plot the power. The power will be some, the red line indicates the power. And this is called as the peak power. One more interesting thing you have to understand that in majority of the operations from a cell, we will operate the cell at 0.6 volt. We want operate maximum voltage or we want operate the minimum voltage. What we will operate? We will operate at 0.6 volt. If you are considering 0.6 volt, what is the power? That is the net power that we are considering when we are using the fuel cell stack. The next one, I am going to explain the different types of losses which is there in a fuel cell. So, according to thermodynamics, we know that there will be some, this is the maximum, there will be some enthalpy there. So, there are three regions there. You can see that there are three regions. Activity means when hydrogen and oxygen reaches the surface of the membrane, how easily it is being converted to H plus electrons. This is what talks about the activation. In majority of the cases, the activation region is the first portion. You can see that this is the activation. This is the energy. There will be some losses in activation. And after that, the ohmic losses. What are the ohmic losses? When you assemble it, when you fabricate the MEA and everything, there will be some losses. This is called as ohmic losses. And when you are operating a fuel cell, you can see that we have to operate in this region. This is the range of operation of this fuel cell. And after that, we call this the mass transport losses. Sometimes when hydrogen reaches this membrane, not only this H plus, some of the H2 gas will transfer through this. There will be some losses because of that, which is called as mass transport losses. So there are three major losses in a proton exchange membrane fuel cell, which are called as activation losses, ohmic losses, and transport losses. Based on the range of operation we have designed, so in majority of the cases we will use this 0.6. The ohmic loss region where we are operating a proton exchange membrane fuel cell. The next one, the basic thermodynamics. We know that enthalpy change will be, so entropy will be delta H minus T delta S. Based on that, I got this 1.23 volt. So hydrogen, what is the enthalpy of the entropy, and enthalpy is being given when it is being formed. What is the enthalpy change, entropy change, and also the free energy change. So ideal performance is being shown in the figure. So real crossover will result in these mass transport losses. Ohmic losses will occur is because of this clamping and everything. Activation loss happens only because of this activation time taken by the catalyst. So these three are the major losses when we are considering the polarization curve. So I think all of them are getting the concepts. So we start from the components, component by component. Now we are explaining the principle, and after that how will we evaluate the performance. So there are three losses when you consider. How will you? So if you're even asking, if you have a membrane electrode assembly, we have to analyze its performance. Only polarization curve was initially present. Now we have a technology called as EIS. It's like an X-ray. How the electron transfer occurring inside. This will help us to understand these three resistance very easily with the help of this EIS, electrical impedance spectroscope. This is the current technology that we are using to analyze a membrane electron assembly after the fabrication. The next one, what is activation loss? I told you that catalyst will reduce this activation energy. So we need some catalyst. Why we are using catalyst? For example, if I'm having this hydrogen and GDL and I'm having a membrane, the process will occur. But what happens? The time taken to split H2 into H plus and electron, the time duration will be very long. So in order to avoid that, some catalyst need to be used to reduce the activation losses, activation energy that is required. So catalyst will help there. So platinum support over carbon is being used by us. So we are considering so many other materials or other materials for this platinum now. So we can see that activation loss, it's happens because of these electrochemical reactions. It happens at the three-phase boundary region. In a long duration, if you are opening, the catalyst will degrade. This catalyst degradation will also affect the performance of the fuel cell. This is also considered under this activation losses. So when you consider platinum, so less platinum catalyst is that currently that we are working on. So ohmic loss, I told you that as the potential increases, this is the ohmic loss graph. What happens is that whenever we are assembling that, there will be some internal resistance will be there. This internal resistance offered by these materials produces this ohmic loss. So when you consider three different layers of the catalyst, there is there, GDL is there, bipolar plate current collectors are there. So there will be some losses. It is called as ohmic loss. Then there is an ionic conductivity and membrane is there. There will be some losses. So this contact resistance, this thermal management, this all is a factor which this controls these ohmic losses. Then concentration loss is very simple. Hydrogen passes through the membrane. We know that proton exchange membrane is that part which transfer only S plus. But if there is hydrogen, if it transferring through that region, we call it as concentration loss or mass transfer losses. This will also reduces the performance of a proton exchange membrane fuel cell. So high current densities happens. So it depends completely based on the porosity and permeability of GDL and membrane. So if there is a small hole in the GDL, it will be nanoscale or picoscale. We are not able to see. There will be losses in through this membrane. There will be some flooding. If the flooding occurs also, flooding means water is being produced and water gets concentrated here, and the overall movement of water is not possible. That affects this. Then microporous layers are being reused to reduce these type of concentration layers. Before this GDL, we will provide some microporous layers. Through the microporous layer, this H plus H2 has to go, so we can reduce the concentration loss by amount by using these microporous layers. So we talked about this. How will you evaluate the performance of a fuel cell? We use polarization curves. When you consider polarization curve, three losses are there: activation loss, ohmic loss, and concentration loss. Activation is because of this platinum. Then ohmic loss because of this assembly. Concentration because of this GDL permeability or naphthalene permeability, some issues. So now I'm going to explain how will you make a fuel cell stack and fuel cell stack. What are the facts that you have to understand? So if you are considering a single fuel cell, we already told that it will produce about 1.23 volt. So 1.23 volt we can operate when you are fabricating a cell, because of the losses we will get about 0.9 to 1 volt. And 1 volt we won't operate the machine. We will operate 0.5 to 0.6 volt. Okay. So if you are operating at 0.5 to 0.6 volt, so if you are considering cell voltage, it is independent of cell size. What happens to current? Current depends upon the cell size. Cell power, what is power depends upon? Power depends upon the cell size, because the active area depends upon the power. So as the active area, if we have to increase, it has to increase the current. That means we have to stack the cells so that the power will increase. So in order to increase the power, what we will do? We will connect the cells in series or parallel. Parallel won't increase the power. So what will we get? We will add the cells in series. That is what we call as fuel cell stack. Okay. So if you know the same concept, if a series connection, voltage gets added up. If it's a parallel connection, current gets added up. So we know that if the cell is having a 0.6 volt we are operating, if we are having 10 cells, the operating voltage will be 60 volt. So majority of the connection we will use series connection so that the voltage gets added up. So this is the structure that we are employing for a fuel cell stack. In fuel cell stack, what we have is, we will say that bipolar plates. Instead of this monopolar plate, here you can see that I'm having this flow field in only one region. We call this single cell and this is called as monopolar plate. If we have to make a two cell arrangement, what we will do is that we will make a bipolar plate in which anode will be fabricated one side, cathode will be fabricated in other side. So this is the structure when we are connecting in series, and this is called as bipolar plate. Since we are using bipolar plate, again the structure or the size of the fuel cell can be reduced. Here you can see that hydrogen goes through this region. So hydrogen dissociates, H plus is being produced. So 2H is here, electron combines, and water is being produced. So fact is that the electron produced from this region moves to the next region. You can see the basic working that I explained earlier. The same function, but here only thing is that when we are fabricating or when we are considering a fuel cell stack, bipolar plate are being used in between them. Fuel cell system that we are considering. So when you are considering a fuel cell stack, currently what happens is that no one is commercially fabricating fuel cell in our market. What we are doing is we are purchasing from some other foreign countries and we are developing a balance of plant for that. What is the balance of plant? Fuel cell, we have to provide a hydrogen sac. Based on the capacity of this fuel cell, we have to fabricate the hydrogen tank. Based on the sensors need to be produced, we have to provide the humidifiers. These all arrangements. Hello? Any doubt? Any doubt?
No, sir. No, sir. Proceed, sir.
So the balance of plant is a crucial factor which controls. What is the balance of plant? The balance of plant means if we have a system, we have to produce, we have to supply hydrogen there, we have to supply oxygen there. It's not a simple task. From the hydrogen tank, we have to use some humidifiers. Humidifier means it is being provided with water content, so that to transfer H plus from one region to another region, initially this membrane electrode assembly must have some water content there. So humidifier will be provided there. So some compressor are being used, some coolers are being used. So these all structure is called as the balance of plant system. If you go this IIT Madras, they are having a 50 kilowatt fuel cell stack now. They are developing the balance of plant now. So here we are having 3 kilowatt of fuel cell stack and a 7 stack test station and 750. So if you observe these machines, you can see that there will be a well-designed engineering there. That means there is a balance of plant. Means we have to, based on the amount of hydrogen, oxygen, we have to design the tank, we have to design the humidifier, we have to design this current, everything. The flow path we have designed, everything that we have designed. So this is a crucial thing that we use in when you are considering proton exchange membrane fuel cells. Currently, none of them are, no company is being fabricating fuel cell. What they are doing is that they are importing from some other countries. They are just designing a balance of plant now. So many companies are there. It's in institutions also. So all the institutions need stacks, but they are not ready to fabricate. So it's very costly. So many challenges are there. So they are commercially buying from some companies, and they are just developing a balance of plant for them to study the different parameters in it. So this is all about the system. So here you can see the hydrogen tank. Then hydrogen is purity is being, there will be a valve. Then it is set to humidifier. Then it is being provided to this fuel cell stack. Fuel cell stack, the temperature will be very high. So in order to control that, we have to use some water separators, water tanks, everything. One more important fact is that if you are making a fuel cell stack, if you are fabricating a 2.5 kilowatt or 5 kilowatt fuel cell stack, what happens is that the temperature produced will be about 2,300 watts, close to the power generation. So how will you manage this thermal management? So what you usually do is that we are having this graphite plates. In between this graphite plate, we will provide some cooling plates, and we will provide some ethylene glycol materials to circulate current. We will use some heat exchanger mechanism there to take the heat out. This will reduce the overall heat of the region. That's how we will improve the performance. If the temperature is above 80 degrees Celsius, the performance of the proton exchange membrane fuel cell will decrease. So we have to offer the temperature always between 60 to 80 degrees Celsius. Okay, this is all about the basics of proton exchange membrane fuel cell. Then why and where we are using this? So we can see that a fuel cell bus is in Delhi is there, and stationary power generation we can use, and portable mobile phones, etc. How we can effectively use that, we are researching on. So currently we are having some fuel cell bikes available in our market. So conventional lithium-ion battery, if you are considering, and what happens if you are using some alpha fuel cell bikes in the market. So these are the different commercially available fuel cell electric vehicles. So Hyundai and these are 2018, 2018. Many vehicles are in our market, but commercially you are not increasing the production because of this hydrogen production. So hydrogen production is a very, very important task. So they have to use green hydrogen. The cost is being reduced as the maximum supplies need to become, then only we can commercially say. For large trucks and everything, we are using this hydrogen fuel cell. Why? Because the carbon dioxide pollution compared to other cars and vehicles, the trucks is having large amount of carbon dioxide production. So fuel cell cars and fuel cell trucks is a major research area now. All the engineers have been working on. Instead of cars, fuel cell trucks and large duty vehicles or heavy duty vehicles. So this is Toyota Mirai, which is launched in 2014. So you can see that about 10,000 to 50 being sold. So for no carbon dioxide is being produced, completely run under fuel cell. So for example, if you consider the carbon dioxide 0 gram, for 0.84 kilogram will give you 100 kilometers in Hyundai Nexon. So 3.5 liters is used for 100 kilometers in this Hyundai Mirai. So the fuel cell cars, the Mercedes-Benz dealers of fuel cell cars, this Honda Clarity fuel cells are Hyundai iX30 is also now fuel cell cars are coming into the market. So if you are considering fuel cell buses, many of the regions you can see that the number of fuel cell buses are increasing. I told you that why the number of fuel cell buses are increasing, because for the emission produced from a large emission production would be compared to the buses, compared to the cars, 10 times or 100 times is high when you are considering buses structures. So all the countries are promoting these large vehicles, heavy duty vehicles using fuel cell technology. In one of the study which is being under in our institution is that we are using this electric vehicle is there with the electric vehicle plus fuel cell. They are using as a range extender. Not only using this fuel, instead of using completely dependent on fuel cell, we are using fuel cell as a range extender. So you have to understand on that fuel cell we can directly use. There also we have to use some electric batteries there. So how we can reduce the size of the battery if we are using fuel cell? That's another research area. So fuel cell buses. So this is developed by collaboration with ISRO. Cochin shipyard developed actually a ship which is now running in Kashi, I think. A ship which is completely powered by fuel cell, hydrogen oxygen fuel cell. The same technology which is being employed there. The complete power is being run, powered by this fuel cell which is developed by Cochin shipyard. So fuel cell buses. So you can see that a zero emission will be there. So here hybrid fuel cell vehicle is being produced. So one of the study is that from Kochi to Trivandrum airport. So this BPSL is planning to introduce some fuel cell buses. Kochi to Trivandrum. I think the next year or coming year, the hydrogen fuel cell buses will be actively running from Kochi to Trivandrum. So hydrogen plants and electrolyzers are installed there. So it's about if you saw this miniature version into a large scale there, if you visit this electrolyzer sites and everything, it's close to the airport. Then we know that we can effectively use them in this fuel cell mobility area. This structure is very, very important. So I told you that how will you produce this green hydrogen production? So now some of the researches are being conducted on seawater electrolysis. If you are able to produce seawater, from the seawater, if we are able to convert this hydrogen, it will be a milestone in the era. How will you convert the seawater to from seawater? How effectively we can produce hydrogen without using any carbon dioxide atmosphere? So hydrogen storage is another issue. So because of the type 1, type 2, type 3, type 4 different types of cylinders are being used now. They are very costly. Composites are being used. If you are using composites, it's very costly now. So if the number of vehicles will increase, automatically the pressure will go down. This is what we are thinking about. Hydrogen utilization. I talked about fuel cell. One more thing is hydrogen ICE, that is internal combustion engine. So one of our co-institution, which is PSG Tech, they are working in hydrogen engines now. So hydrogen engines, when we consider, the only problem with this the performance related to the knocking. So hydrogen is a fuel which is having high flammability. It's flammability is very high. So it is when you are using that, how will you control the knocking is a critical issue when you are considering hydrogen utilization for IC engines. So no policies are being introduced by India now. Currently, so many companies are being creating these policies so that in 2024-2030 there will be a market for hydrogen. So hydrogen infrastructure is a creation, I told you, the balance of land, like creating an infrastructure, making the awareness. So last year, so 90 something, so how will you make the humans, how the people aware that it's very user friendly, then only we can use it. So we are using some machine learning approaches, etc., to how will we effectively impact the climate change and everything. So in order to reduce the safety is a major issue. When we are talking about hydrogen, all will talk about safety. So sensors, how will you develop the sensors so that it can be effectively used? So if you have to use a power conditioning, some balance of plant which is being effectively done. So these all are the research areas. So hydrogen green production, some of them I can see seawater electrolysis. So hydrogen storage is a research area. How effectively you can use hydrogen utilize in fuels and IC engines. So this AML, machine learning or artificial methods doing the sustainability. Then how will you develop the sensors for producing hydrogen safety? These all are the areas for engineers. So we can work on this. So in our campus, we are working in hydrogen utilization. Hydrogen production is occurring in PSG is in close to PSG Tech, and is also in Coimbatore. So these two areas I'm working on, this green hydrogen production and green hydrogen utilization. These two areas I'm working on now. So conclusion is that there are so many problems are there. Platinum, the main issue is the platinum. How will you reduce the amount of platinum by using some other catalyst? How will you reduce the cost, and how will you improve the how will you improve the performance? So then, if you are using catalyst, we are using carbon as support materials. Any other support materials possible that we can study. How will you increase the durability of the machine? How will you develop membrane indigenously? If you are able to develop a membrane indigenously, all cost will be reduced. If you are able to develop a catalyst in India itself, we are able to reduce the cost. So all of them are working. But what happens is that no one is ready to invest small amount of R&D because in many of the companies, totally doubt we have to say that we are 15 years behind compared to other foreign countries. They are manufacturing the fuel cells, they are commercially selling that. If you search to Amazon, you will get 2 kilowatt, 5 kilowatt stacks available. So indigenously, no one is ready to fabricate. It's only issue. They are buying from some other foreign countries. So how will you change this? In other nations, we change the size of bipolar plates. How will you change that the stainless steel has some other very thin plates? It's another issue. How will you change the end plates to some composite materials? How will you manage the thermal management? There are so many tasks are there. So compared to other area, this is a developing area, this is a booming industry. Each state is developing. So within days, we can see that there will be a considerable change in the industry within 20 years. Now it's a booming industry for electric vehicles. Now after 20 years, the electric vehicle will be, if all of them will talk about how will you stop this electric vehicle, the lithium ion battery, how will you stop it is harmful to environment. Someone starts saying like that. During that time, these fuels will come into market. For 2030 or for 35, we are talking about these fuels in the market in India or other countries. In China and Japan, Canada, some of the countries, fuel cell buses are there, many cars are there. How effectively we can in the Indian market? When you consider Indian market, your Indian drive cycle is totally different compared to other countries. So how we can do research on that field also? How will you use this fuel cell in our Indian drive cycle? Okay. So this is my professor, Dr. Manoj Kumar Sir. So he's from IIT Madras. So under him, I am working in this project for the last 2 years. Only 3 months are there. We are currently working the development of this stack. So we optimized. We are getting close to 1.24 watt per centimeter square, which is close to Toyota Mirai's performance. Toyota Mirai they are getting 1.33. Now we are able to develop a membrane electrical assembly which is literally give us about 1.24 watt per centimeter square. So if there is anything there, you can just visit us. It's in all of our, if you can do, if you have to do any collaborative or anything, you can just visit our lab, or you can just mail to my sir Gabe. He will there. He's working completely working on this fuel cells.